Now, whenever I have two different coordinate systems, when I have two different people who see the coordinates, see the coordinate system in different ways, right? Just like we had before. Somebody might think in terms of U1, U2. Somebody might think in terms of V1, V2. Now, when I refer to a point or a vector in space, right, we're both talking about the same one if we use this relationship that we have between these two guys. And so we need to give this a name. We need to give this matrix a name because this matrix is really giving us a relationship or helps us to transition from one coordinate system to the other. I can use this matrix to transition from one coordinate system to another. And so what we're going to do is we're going to give it a name. What's a good name for this matrix? We should call it let's call it a transition matrix. So definition. Definition. Yes. I need to go to the next page. Here it is. I have capital P, subscript B to C. Okay. B to C. This is going to be equal to, or is it C to B? C to B. Oh, I have the arrow going the wrong way. Pardon me. Like I said before, the handwriting is really small here. It's going to be C to B, but the arrow goes the other way, C to B, right? And we'll see right now. The P subscript C to B is equal to this matrix that I have right here. A, D, B, E is called the transition matrix. From C to B. And there's a reason why we write it this way instead of having the arrow going from left to right. We have it going from right to left. It makes it easier to see that we're taking in C and we're outputting B. That's what we're doing. So we're taking in C over here. We're outputting B on the right-hand side. So it's called a transition matrix from C to B. And I can say that the transition matrix from B to C is just going to be the inverse of that. So the transition matrix from B to C is going to be denoted with P from B to C is equal to the inverse of the transition matrix from C to B. Okay, it's inverse of that. So you'd be looking at the inverse in this 2x2 case, A, D, B, E, inverse. Okay. It's the inverse of that. And let me do it the way I have it in my notes. Put the inverse like that. Okay. And I want you guys, and I have another thing in my notes that I wanted to say before we kind of move on. Let me erase this though. I think hopefully you guys got the idea behind the change of basis and what we're doing there. But I have a little note. Note the transition matrix from C to B is really equal to, when you look at it, it's just the coordinate vectors right here. If you look at this, this is AB and this is DE. So this is, remember here we have AB, we have DE. It's essentially just the coordinates of V1 and V2 relative to B, but going vertically down. So I'm going to have V1, B, comma, V2, B, right? Going down, right? So essentially it's just the coordinates of V1 and V2 relative to B is what we have here. So the transition matrix is always going to in this case, be that way. So, finally, I know this is probably a mouthful, but hopefully you guys are still with me. All right, so let's write down, what's the steps to finding the transition matrix? Matrix from C to B. Step one. Step one is that we want to write the vectors in C in terms of the vectors in B. Okay. And this is what we did right here, right? We have V1 in terms of, and V2 in terms of our basis B is going to be these coordinates that we have here. Find the coordinates. Step two, okay, is that the columns of the transition matrix are the coordinates found in step one. Okay. So just two steps. What we need to do is we need to write the vectors in C in terms of the vectors in B, find the coordinates. Step two, the columns of the transition matrix are the coordinates found in step one. Now, let's not get too hung up in basis C and B. What we're essentially saying, write the vectors in our old coordinate system in terms of the vectors in the new coordinate system. That's what we want to do, okay? Right, so you might know the vectors in the old coordinate system, and you want to write those vectors in terms of the new coordinate system. Find those coordinates, right, just like we did there. And step two, the columns of those of the transition matrix are going to be the coordinates that we just found in step one. Okay, that's all there is to it. And this works no matter if this is Euclidean, Rn, R2, R3, R4, or if it's another type of vector space, or like polynomials or matrices or anything like that. Okay, let's do an example. Let's do an example. Okay. And these are all in the PowerPoint as well. So hopefully you guys are looking at the PowerPoints as you're doing this. Just in case sometimes my handwriting is not that great. I try to make it as good as I can, but sometimes it's not. It's not that great. Let B equal U1, U2. It doesn't matter which one you call U1 and U2, right? Those are just placeholder names. Equal, and I'm going to write my vector 1, 2. And what do we have here? Negative 1, 1. And C equal to, here I have another basis, V1, V2. Equal to, here I have 1, 1. And 2, 1. I want you guys to notice that these vectors in both B and C are linearly independent, right? I have two linearly independent vectors in B. I have two linearly independent vectors in C. So therefore, they must be a basis for R2, okay? Be a basis for R2. And I want to find the transition matrix from C to B. Okay. Find a transition matrix from C to B, and then we'll do part B in just a second. So this is A. I want to find a transition matrix from C to B. So what we need to do is we want to be able to first, right, since we're going from C to B, C is our old coordinate system, and we're going to go to our new coordinate system, which is B. So I need to write the vectors in C in terms of the vectors in B. Okay, so that's what I want to do. So step one, write vectors in C in terms of B. Okay. That means that if I take 1, 1, it has to be equal to A times, what do I have? 1, 2, plus B times negative 1, 1. And I want, what's the next one? Let's say other vector in C. 2, 1 equal to C times 1, 2, plus B times negative 1, 1. And I want to find A, B. Oh, this should be it. This should be D and E, right? Or whatever you want to call it. And I want to find A, B, D, and E. Well, you know how to do this, right? We've done this type of problem multiple times, right? This is just a system of equations. I'm just going to show you how the first one would look if you just toss this into your calculator, right? Put it right in augmented matrix. So I have 1, 2, negative 1, 1, dot, 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 1, 1. This one would be good. 1, 2, negative 1, 1. Good. 2, 1. And I want to do reduced row echelon form, right? I'm not going to go ahead and do all that. You guys can do that at home. But I can do the reduced row echelon form of this to figure out what A, B, D, and E are. If I did it correctly, I got A to be equal to, what do I have? A is equal to 2/3, B is equal to negative 1/3. So we'll say AB. I have this is equal to 2/3 and negative 1/3. And D and E is equal to, what do I have here? I have 1 and negative 1. And you can check it out for yourself, right? Take 1 of this vector plus negative 1 of this vector, do you get 2, 1? And the answer should be yes, right? So here are my two coordinates, right? This is the coordinates of V1. V1 with respect to B. And this is V2 with respect to B. Right, so now that we've done step 1, we found the coordinates of V1 and V2 with respect to B, right? So we wrote the vectors in C in terms of the vectors in B. Step 2, they might actually be able to see you. Step 2 is step 2 is write the transition matrix. Sorry, my son is being a little bit silly, so hopefully you didn't see what he was doing. Transition matrix. My son is silly because I'm silly, so that's kind of what happened there. It's my fault. So the problem, the transition matrix from C to B. Okay, this is going to be equal to, right, our our coordinates, 2/3, -1/3. And then the next one is 1, -1. So this is our transition matrix from C to B. If I want to, I can find a transition matrix from B to C by taking the inverse. So let's do that. B to C. That'll be the inverse of the one we just got to doing, the transition matrix from C to B. And what you end up with is 3, 3, -1, and -2. Okay, so now these two transition matrices allow us to talk back and forth between two coordinate systems, right? So the coordinate system based on the vectors, the basis B, can now talk with the coordinate system based on the vector C, right? So this one, so if C said something, right, this will translate what C said in terms of coordinates to B. So if B says something, right, in terms of coordinates, this matrix will translate what B said into what in terms of C, right? So I can talk back and forth between the two. You can think of this as almost like a language translator, right, between French and English, right? Google Translate, right? So Google Translate goes back and forth. So I can talk in English and it'll spit out French. I can talk in French and it'll spit out English. Well, hopefully some type of English it'll be able to spit out. Now let's look at B then. I'll put it down here. B. What do I have? I gotta find it. Find the coordinates of X relative to B if the coordinates of X relative to C is equal to -3, 5. And then I have a C. Find the coordinates of Y relative to C if Y, the coordinates of Y relative to B are equal to 1, 1. Okay. So essentially, I know what the coordinates of the vector X is in terms of C, but I have no idea what the coordinates of the vector X are in terms of B, right? So I want to be able to figure that out. And here, I know what the coordinates of Y are in terms of B, but I don't know what they are in terms of C, and that's what I want to be able to find here. So that's what I want to do. Erase that. Gotta make sure I have enough power on my camera there. I think I'm doing well so far. Okay. So far so good. So let's do that, right? So I have the coordinates of X in terms of relative to C. So I'm going to write that in terms of B. So which one of these guys do I have to use? Well, I want to go from C to B, so I'm going to use my transition matrix, my first one that I have here. So what is going to be, let's say write B here. What is X relative to B? Well, what are the coordinates of X relative to B? And that's going to be equal to my transition matrix. 2/3, 1, -1/3, -1. Before I do this step, let me just show you guys why I like the way we have the arrow pointing. Because when we think about this in terms of symbols, right? So I have C to B, X to C, right? So say we take the coordinates of X relative to C, take that and bring that to B to get my B here. So I have X to B. So from C to B. Can you see C, C, B, B? Right. So anyway, just kind of nice to see that. So let's see what do we have here. We have 2/3, 1, negative 1/3, negative 1. And my coordinates of x relative to c are negative 3 and 5. And when you do that, when you multiply those guys together, I have 3 and negative 4 here. Before I keep going, I would like to mention the fact that now I can, what is x? What is x in this case? What is the vector x? I know how to get to x. I know how to get to a point in space or get to this resultant vector, but what is that vector itself? Now I have two ways to be able to figure that out. I can either use the coordinates of x relative to b, or I can use the coordinates of x relative to c. Let's use the coordinates of x relative to b. Okay. So I'm going to say x is equal to, relative to b is going to be 3 times v u1, which is going to be 1, 2. Minus 4 times u2, which is going to be negative 1, 1. Okay, so this is u1, this is u2. Okay, let's see if I can do this in my head. Oh, math. 3 plus 4, I think that's 7, right? 6 minus 2, 6 minus 4, that's 2. It's 7, 2. Or if I wanted to, I could use the coordinates of c to get to x, right? So let's look at x using the coordinates of c. So we have x is equal to, let's see, what are the coordinates in terms of c? I have negative 3 times v1. v1 is 1, 1. Plus 5 times v2, which is 2, 1. Okay. So if I read across, I have negative 3 plus 10, that is 7, right?